Hi, it's Dr. Iqbal. I warmly welcome you to my YouTube channel, Organic Chemistry with Dr. Iqbal. Today we will be discussing about shapes and orientations of orbitals, that how the orbitals look like in space and how many they are. But first of all, we have some unfinished business. The spin quantum number, we have to explain that we have to finish them too. So what it tells us and what are they? It's again a number, and the spin quantum number is represented by small s, small case letter s. It tells about the spin of electron. It just tells us that whether an electron is spin up or spin down. It has two values, plus half and minus half. One value is for spin up, electron spin up, and the other is for electron spin down. Now, as I mentioned previously, that all the three quantum numbers, just like the principal quantum number, azimuthal and magnetic quantum numbers, they were the direct solutions of Schrodinger wave equation, but this one is not. The reason is that those three quantum numbers just told us, or just told us the position of an electron with respect to the nucleus. Let me draw something on the board that you will understand. Suppose this black dot, this is a nucleus. These are some shells. How many they are in? Okay, let's say the nucleus should be right in the middle. Okay, this is a tentative or old model of an atom. This is K shell, this is L shell, this is M shell, and this is N shell. Or 1, 2, 3, 4. Okay, and let me draw some electrons. Suppose this is one electron, this is another electron, this is another electron, and this is another electron. Now, the position of an electron. I told you that this spin quantum number doesn't tell anything about the position of an electron, but the position of an electron with respect to the nucleus. As you see here, if this thing is the nucleus, this dot, these are the electrons. In K shell, the electron is very near to the nucleus. In L shell, it's a little bit farther away, and in M shell, it is more farther away, and in shell, it is much more farther away from the nucleus. So its position relative to the nucleus is different. But the spin quantum number just tells us what? It tells us about the spin of an electron, whether it's up or down. So it doesn't tell us about the position. For example, let me give you an analogy. If someone wants to visit someone's house, so if someone wants to know someone that where he lives, so he first confirms the city, and then he goes to the block where he lives, and finally to the room or the apartment where he is living. He has this information is sufficient to know where the person is present. Now it's up to the person, but if he is standing straight or standing upside down, it is not concern of the person. Just like it is not the position. It just like it doesn't tell anything about the position of the person. I don't think so that analogy quite fits here, but anyhow, this thing is very good. That this electron is farther away, and it is what thing tell us that this electron is farther away? Principal quantum number or the azimuthal quantum number tell us? The azimuthal quantum number just tell us that in which shape the electron just lives. Like this, it's a p orbital. Suppose, so the electron revolve here, 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 here. So it tells us that, and this is the nucleus. So it again tells us the position of an electron from the nucleus, whether it is, if it is here, so it with respect to it is here, with respect to the nucleus it's at this distance. If it is here, so with respect to the nucleus it is at this distance, and so on. Now let's come to the shape and the orientation of orbital, which we want to discuss because it's very interesting and important topic in chemistry, and it's very much important for the beginner students. So first of all, let me tell you that azimuthal quantum number, what it was telling us about s orbital, it just gave a one value 0, which this value as the spin azimuthal quantum number just provide us with the numbers. All the quantum numbers provide us with some numbers, but this number is interpreted as s orbital or spherical orbital s. Now for L is equal to 0, M is also is equal to 0. What does this mean? It means that it has just one orientation possible. It will be clear when we go for the three-dimensional objects. Now, so for L is equal to, as you know, that plus minus 1, so it is equal to minus 1, 0 and plus 1. Now there are three solutions. It tells the magnetic quantum number tells that the dumbbell shape, the dumbbell shape, which is called as the p orbital, they are 3 in number and they are oriented in such a way that they are oriented like px, py and pz. Suppose this is px, this is py and this is pz. Now let's move to the L is equal to 2. Now we are talking about d orbital. So magnetic quantum number value are 5 minus 2, minus 1, 0, plus 1, plus 2. 1, 2, 3, 4, 5. It just tells, the magnetic quantum number tells that there are 5 orientations possible. So you can also interpret this that there are 5 compartments available for electrons to live, and there are 5 ways that they are arranged. Each one is arranged differently from the rest of the others. So it will be clear in a moment. Okay, let me tell you or show you something. Suppose this is, what is this? This is a balloon, but it is spherical. This is round, so let's give us, it's analogous to s orbital. Now according to the magnetic quantum number, its value is 0, so it doesn't have any orientation. So it just have one orientation. If you view it from this angle, you will see that you will think that this is a sphere. If you are looking now, it's a sphere. In any direction when you look at this, you will see, or you will find it in a spherical form. Now let's move to another thing, the p orbital. What a p orbital is? The p orbital is just made up of 2 spheres or oblong spheres, eggs-like things, but these are also 3-dimensional. But now here the thing arises, because the magnetic quantum numbers said that it can have 3 orientation. You can have basically the minimum 3 orientation are possible for this thing, and these orientations are just like this. Now you can view it. This is one direction, now it is in another form, and now it is in another form. So magnetic p orbitals, they exist as px, py and pz. So to understand these p orbitals, their orientation, we need to understand the Cartesian coordinate system. And majority of you may know that what Cartesian coordinate system is. For those students, it's just a review or revisiting of the concept, and for those who are learning it, for those who are seeing it for the first time, it's a new thing for them. Probably most of you might be knowing it. So this is x, y and z. Okay, but as you know that this is also having minus x or x prime, also having z prime, and this thing is also having y prime. But now this become even more complex or complicated to comprehend or to conceive that what actually this thing is. So to understand, to make you understand, I have just created some models because nowadays the country is locked down because of coronavirus, and therefore I have handmade tools, handmade 3D direct source, handmade. I have a handmade a Cartesian coordinate system. This is the one. So this is x, this is minus x, this is z, okay, and this is minus z, this is y, and that is minus y. Is it clear? Yeah, it might be clear or not, but I have tried and you need to appreciate it. So let me tell you about the px, py, pz orbital. Px orbital just lies on x axis. Okay, py on the y-axis and pz on the z-axis. Okay, so let's see it. These poor balloons. Okay, now this is a Cartesian coordinate system. Now how the 3p orbitals px, py, pz, they are arranged in a nucleus, because the nucleus in an atom is a small thing, so they are just like this. They are arranged in this way. This is the px orbital. It lies on the x, starting from x, and on the minus x. This is the pz orbital, and this is the py orbital. Okay, your people might be getting it. But how these three orbitals are arranged? Because they are not separate from each other, they are in a combined sort of form. So the px orbital is like this, okay. The py orbital is like this one, this. I think that in the camera you might be seeing, and this is the pz. So these three orbitals are like this. Okay, so this one is the green one is pz orbital, this one is the py orbital, and this red one is the px orbital. As I explained the p orbital, how they look like. Now once again let me try to explain it on this axis. The px orbital, it lies on the x-axis just like this. Look at this. This is the coordinate system. This is x, this is the y, this is z, and this is x prime, and this is z prime, this is y prime. So how it looks like it is just present on this axis. Okay, this is the other thing. What about the py? Now the py is arranged like this, because I am writing about the two-dimensional things. I am writing on a two-dimensional board, so it's quite difficult to write the three-dimensional, but you understood it. And the other orbital is like this. This is one lobe and this is the other. Okay, these orbitals look like this. Now coming to the d orbital, the d orbitals are a little bit complex, and as you know that the magnetic quantum number m, how many values it gives? As L is equal to 2 for it, so magnetic quantum number is like this, plus 2, sorry, so minus 2, minus 1, 0, plus 1, plus 2. So 1, 2, 3, 4, 5. There are 5 cabinets or 5 things present. Okay, there are 5 compartments present for electrons, and they are arranged in 5 different ways. Among these d orbitals, the dz squared orbital, it is the simplest type. not in chemistry but in arrangement or in orientation it's very easy that how it is oriented. It's just like this. Shade it or shade this thing. Okay, it's just like a p orbital with a ring around it. So it can be represented like this. Okay, this is the coordinate system, and now this is the orbital. It lies like this. Okay, this is the Bz orbital because this is the z-axis. Okay, and the ring was lying on the xy axis. That it just look like this thing. Okay, got it? As I showed earlier. Okay, on the x-axis. Now the ring lies on xy axis. This is the ring which lies on the which is present on the xy axis, and this thing is inside it. So this is the d squared orbital. Okay, now as these are the orbitals, and how it will look like here in this coordinate system, it will look like this. And this is the ring on the xy axis. Okay, now let's move to the other orbital, which is the other orbitals, remaining orbital of the d, the dx squared minus y squared, the dz square, the dxy, the dyz, the dzx. Let's go to the dx squared minus y squared, dxy, dxz, dyz, and we did this one. Now how they look like? So the simplest one of them among them I think is the dz x squared minus y squared. So I have made some orbitals. As you know that just because of lockdown I have made this by myself. These are the two lobes of the orbitals, and only this dz orbital is different. The rest of the orbitals are double dumbbells. All of them are like this, double dumbbells. Okay, so let me explain the dx squared minus y squared orbital. So let me draw the thing, coordinate system. This is x prime, z prime, z, y, and y prime. Now what about the dx squared minus y x squared orbital? It is just present on the planes or the axes. So this is the dx squared minus y squared orbital. It's present on the x and minus x. Okay, and on y and minus y. Both the lobes are present like this. So let me show you in 3 dimension. So look at this. This is the 3-dimensional thing. Okay, and they are just present like this. Okay, these are the axes. If I tilt it, you may know that how it looks like. It is present on the x and on the y axis. Okay, now let's move to the other orbitals. This one is okay, the dxy orbital. So for the dxy orbital, it's just like this. This is the coordinate system, x, z, y, z minus, x minus, y minus or y prime. Okay, so this orbital is present between the axes. In between x, yx here and in the other lobes, it's just like this. It's difficult to conceive or understand from here. You will understand right here when I show the model or on the my beautiful models. Okay, so these are the x. This is x-axis. This is x prime. This is y. So it is between, each lobe is between the x and the y lobes. Okay, so now this is like this, and you can see it. If I tilt it, this way will give you proper direction. Okay, this is Dxy orbital. Is it okay? Now coming to this orbital is done, xz and yz. Now coming to the xz orbital. So because it will be between the x and the z orbital, axis is now you can because of the time, so I have to show you right here the xz orbital, the Dxz orbital. Now it will involve what? It will involve the x and the z axis only. This is the x, z, and this is the x. So it should be like in between those two. But you have to arrange all the lobes. Look at this. No component is present on the y-axis, and it is just between, each lobe is present between these x and z axes. Okay, now it's done. Now moving to the dyz. Now this is the y-axis, so it will look like dyz will look like this. But from this angle, it's you cannot view it easily, so it's like this. Okay, these were the orbitals, that how they look like in space. So from the conclusion from the quantum number is the quantum number and shape orbital is that the quantum number just tell us that how and where the electron is and in which shape it is living, and how those shapes look like, how those shapes when combined together look like in space. So that was the thing, and those were the orbitals, and we'll meet in the next video. Thank you very much.